Hello chemists, this is Miss Placino and you are watching Screencast 4.4 on molecular geometry. Today we're going to talk about using Lewis structures to determine the three-dimensional shape of a small molecule. Usually when we're drawing covalently bonded compounds and Lewis structures, we tend to draw them as being very flat or very two-dimensional, with all of the atoms of that molecule being in the same plane. It turns out for a number of different molecules that's not the case. Some of the atoms are going to be pointing out towards you, some of them are going to be pointed away from you, and some of them will be in the same plane as the paper. And really what we're going to do today is try to make the connection between what did I draw and what would this look like in 3 dimensions. For better or for worse, this does require just some simple memorization, and we'll talk more about that as we get rolling in today's lesson. Let's take a look at the do now. When multiple atoms are bonded to the central atom, would you expect them to be close together or far apart? Explain your answer. So if you haven't done so already, pause the video, try to brainstorm how you would expect the atoms to arrange themselves around the central atom. All right, let's think about this. When you're going to bond things, I should say bond atoms to other atoms, it's really the electrons that are getting involved in the bonds. So if we think about something like CH4, we tend to draw it looking something like this, as opposed to something like that. In reality, both of these are perfectly valid Lewis structures, but we tend to space out the atoms that are coming off of the central atom as much as possible. If you think about it, you've got electrons being shared in between each hydrogen atom and the carbon atom. We know that electrons are negatively charged, and if you try to put a bunch of them together like we have in this other Lewis structure, you can imagine there might be some repulsive forces between the pairs of electrons. And that's really why we see everything being spread out as much as possible when we're talking about different geometries. We have a theory to help explain this spreading out of electrons, and it's called the VSEPR Theory, and that stands for Valence Shell Electron Pair Repulsion. So valence, because we're talking about the outermost electrons, and repulsion, because we know that the like charges of the electrons are going to be repulsive forces and kind of force the bonded pairs and non-bonded pairs of electrons to spread out. So really, according to the VSEPR theory, shape is based on spacing out pairs of electrons as much as you can. So don't pile up pairs of electrons really close together. We want to try to spread them out because, again, you've got those negatively charged electrons and pairs of them are going to repel other pairs of electrons. From a predicting geometry perspective, we're going to treat double and triple bonds as though they're exactly the same as a single bond. In reality, this is not the case. We know that double bonds have a total of 4 electrons being shared. Triple bonds have 6 electrons being shared. So they're not all the same type of bonds. But according to the VSEPR theory, we're going to treat them as though they are. And this valence shell electron pair repulsion theory is what we're going to use to predict the three-dimensional geometry, or just simply the shape of the molecule. All right, so we're just going to go through the bunch of different shapes that I want you to be familiar with. In reality, there are even more shapes out there, but we'll leave those for AP Chemistry, and we'll focus on the basics. So as you can see, this is called a linear molecule. Hopefully it's pretty obvious why. All of the atoms are in a straight line. So when we're talking about atoms bonded and unshared electron pairs, as it says right here, we're talking about in reference to the central atom only. So if you look at the central atom, and that's always going to be in red, we can see that there are 2 other atoms bonded to the central atom. If I look at the central atom, I see that there are no unshared electron pairs. I don't see any like dots, for example. We'll just erase those. Erase that too. Bond angles, if I was to measure the angle from here to there, I would see that that's 180. And one really good example of a linear molecule is CO2. So just draw that out. Again, remember, according to the VSEPR theory, we're going to treat double and triple bonds as though they are equivalent to single bonds. And that's just going to help us predict the shape. So whenever I see a molecule that has 2 atoms bonded to the central atom and no unshared pairs or lone pairs of electrons on the central atom, it's a very safe bet that that's going to have a linear geometry. Let's make it a little bit more interesting and throw a third atom on there. So now we've got 3 atoms bonded to the central atom. We have no unshared electron pairs. You can imagine it's kind of like a circle almost around it. And if we were going to divide that by 3, we'd end up with bond angles of 120 degrees. If you think about it, what atom do you know is only capable of forming 3 bonds? Hopefully you're thinking about boron. So a lot of our boron compounds are going to be this trigonal planar geometry. Trigonal because if you connect them it looks like a triangle, and planar because all of these atoms of this molecule are in the same plane. Put a star next to tetrahedral. This is one of the more important geometries. In a tetrahedral molecule, we have 4 atoms bonded to the central atom. And again, no unshared pairs of electrons. Tetrahedral because we connect everything. We could see that the atoms are oriented, everything I guess but the central atom, are oriented to the corners of a tetrahedron. Rid of that stuff. The bond angles work out to be 109.5 degrees. And a lot of our carbon-containing compounds are really good examples of tetrahedral. Something like methane, CH4, is going to be tetrahedral in shape. Let's start taking off some of those bonded pairs of electrons and replacing them with an unshared pair. That's what that kind of like blue cloud with the 2 dots in it are supposed to represent. That's a lone pair or unshared pair of electrons. Because the electrons aren't shared between another atom, they're just kind of like exposed, and they're going to take up more space than a bonded pair. So if we look at the Trigonal Pyramidal geometry, we can see that there are 3 atoms bonded to the central atom, and then we have this unshared pair of electrons. You might look at this and say it should have the same bond angles as tetrahedral, and you're kind of on the right track. But due to the fact that this cloud of electrons is going to take up more space, it's going to kind of push all of these bonded atoms a little bit closer together. So we're going to see bond angles that are less than 109.5. A good example of trigonal pyramidal molecules are those containing nitrogen as the central atom, such as ammonia. We know that nitrogen has a Lewis dot diagram that looks like this. So you can imagine when it bonds with hydrogen, we'll get that shape, and that's what trigonal pyramidal is going to look like. You might remember me saying in class that it's really important that you remember to draw your unshared pairs of electrons on there. Well, this is why. All of a sudden the geometry is going to change if you don't draw that unshared pair. With it, we see the trigonal pyramidal geometry. If I take those off, I get trigonal planar. So it does make a difference. Make sure you're drawing Lewis structures correctly. The bent geometry is another variation of the tetrahedral. So we've got 2 atoms bonded to the central atom, and now we've got 2 unshared pairs of electrons. So again, you might predict 109.5, but since we've got these 2 big unshared pairs of electrons, they're going to squish those 2 bonded atoms closer together, and we're going to see something that is substantially, that's what we mean with that less than signs, one after the other. And what are we thinking we say substantially? Maybe around 104 or 105 degrees. And the most common example of this is water, H2O. So water always has those 2 unshared pairs of electrons. So sometimes it's better to draw it at 90 degrees instead of drawing it as a linear molecule. Technically both are correct, but this representation makes it a little bit easier to see that we're going to have an angle that is not equal to 180 degrees. Next up, we've got trigonal bipyramidal. Trigonal for the triangle shape that's going around here. And then bipyramidal, the prefix bi means 2. There we go. So you have like 2 little pyramids, one on top of the other. Okay. So in this case, we've got 5 atoms bonded to the central atom. We don't see any unshared pairs of electrons. The bond angles work out to be 120 degrees between these 3 atoms that are on the same plane, and then 90 degrees between like the top atoms, I guess I should say the top or the bottom atom and that triangle. If you think back to what we talked about in the previous lesson with expanded octet, which element do you know is able to expand its octet and incorporate up to 5 atoms bonded to it, or 5 pairs of electrons, for a total of 10. Hopefully you're thinking phosphorus. Phosphorus can expand its octet, so something like PCl5 is going to take on a trigonal bipyramidal geometry. And the last one that I want to talk about is octahedral. In this case, we see 6 atoms bonded to the central atom, no unshared pairs of electrons on the central atom. You end up with bond angles of 90 degrees all the way around. And yeah, we talked about another element that's capable of expanding its octet and holding a total of 12 electrons. Hopefully you're thinking of sulfur. So a good example of this is SF6. Sulfur can expand its octet to hold all 6 of those fluorine atoms. So I've gone ahead and I've pulled up some practice problems. I'm sure this chart initially looked overwhelming, but we're going to keep chipping away at it a little bit each lesson from here on out. So I've got 8 different molecules drawn. They're correct Lewis structures. And where it says shape, this is where I'm going to try to predict the molecular geometry, or the 3-dimensional shape of this molecule. What you don't want to do is just really get in the habit of referencing that sheet of paper that you've got in your workbook and looking everything up. That's going to help you with the practice problems, of course, but it's not really going to get you ready for the test. You have to kind of just know these. This might be something that's good to put on a flashcard and just kind of practice with those different geometries. So if I look at PCl5, I've got 5 atoms bonded to the central atom. I have no unshared pairs of electrons on the central atom. The only geometry that fits this build is the trigonal, put that on pen, Trigonal Bipyramidal. And feel free to abbreviate. I know I didn't leave you a whole lot of space. Moving on to H2S. I've got 2 bonded pairs of electrons. I have 2 unshared pairs of electrons. Only one geometry was going to work. That's bent. It's kind of analogous to H2O. Move just right across the rest of these. The shape here with 4 bonded pairs of atoms, bonded pairs of electrons to 4 different atoms and no unshared pairs is going to give me the tetrahedral geometry. And the last one in this row, we've got ammonia and H3. I see 3 bonded pairs of electrons to each of the hydrogen atoms and 1 unshared pair. That is going to be a trigonal pyramidal geometry. So why don't you go ahead and pause the video, see if you can figure out that next row of them. And if you haven't drawn them already, I guess you can see what they are, so you can copy it down now. All right, so take a moment and check your work against what we've got on the screen. SO3, that's going to be trigonal planar. I've got no unshared pairs of electrons, and I've got 3 atoms bonded to the central atom. Again, keep in mind that double and triple bonds are analogous to single bonds in this model. PH3 is trigonal pyramidal, actually not kind of, but extremely similar to NH3. PF5, that's going to be trigonal bipyramidal. Doesn't matter what the bonded atom is to phosphorus when it's formed 5 bonds, it's always going to take on that geometry. And finally, SF6, like we talked about in the PowerPoint presentation, is going to have an octahedral geometry, as there are 6 bonded pairs of electrons to that sulfur atom. My suggestion is to go through and keep practicing with this. You have tons of practice problems to work with, and the only way to really get this committed to memory is just to force yourself to draw these molecules and predict their geometries without using kind of the cheat sheet that you put together in your workbook. All right, so keep on practicing, and I hope this was helpful. I'll see you again soon.